Hi. Now that we've discretized our problem, we're ready to move on to our next step, finding the local behavior and finding the local stiffness matrix for each one of our three elements. So you'll recall from previous lectures that we found that the general form of the local stiffness matrix in global coordinates takes on this form. But remember, this is a function of not only the modulus of elasticity, the area, and the length of each bar, but is also a function of the angle each bar makes with the global x-axis. Previously, I suggested that some people find it easier to start out by writing down the various information of what various cosine sines and sine squares and cosine squares, etc., in a chart such as this. So if I was to do this, I would look at element number 1. Element number 1 forms a 90 degrees with the global x-axis. Element number 2 is 45 degrees with the x-axis. And element number 3 conveniently is 0. Since in this particular problem, the stress elements make nice either 0, 45, or 90 degree angles, finding the cosine and sines is rather simple. I can fill this in fairly quickly. Cosine of 90 degrees is 0. Sine of 90 degrees is 1. Cosine squared would also be 0. Sine squared would also be 1. Cosine times sine, well, one of them is 0, so they're both going to be 0. The length of element 1 is, the length was given as 10 feet, but let's keep this all in the same units. And since we've got PSI and the area is in square inches, let's call this 120 inches. We can write this as 3e to the 7, meaning where the e is shorthand for times 10 to the 7th power, and the area, again, is 2 inches squared. And I could do the same for the other two elements. I've already gone ahead and done that. You can see I filled in, this is the same chart I have down here with just all the various information filled in for us. Once I have this chart, it's just a matter of plugging and chugging for each element. I'm going to get 3 local stiffness matrices, one for the element number 1, one for element number 2, and one for element number 3. You can just plug and chug these values into this formula, and what you'll find is that our 3 local stiffness matrices take on these values. Okay? All right, so now we found our local stiffness matrices. The next step is to find our global stiffness matrix.